welcome back to the lecture series on bioenergy. So to start the third week, so we are into module 3, which is also week 3, W3, and in sum total this is the 11th lecture, and in module 3 this is first lecture of module 3. Okay. So, in the last class when we concluded our lecture, we talked about the complete outline what we will be discussing. So, the first thing what we will be discussing in today's lecture will be the outline of electron transport from photosystem 2 to photosystem 1. Then we will talk about how the physical structure of the photosystem looks like. Third, we will talk about the splitting of the water at water splitting cluster, and in between we will talk about the formation of ATP because of the proton gradient which is created across the chloroplast membrane or thylakoid membrane. Okay. So, let us get back to the slides. So, this is where we ended our slides last time. So, this is what we decided we will be talking about, the outline of the electron transport, followed by the formation of the ATP, water splitting cluster, and after that we will talk about the dark part of photosynthesis, which is the dark cycle or the Kelvin cycle. But today we will be concentrating on those three aspects, the electron transfer and the physical structure of the photosystem, followed by ATP formation and concluded by the water splitting cluster. So, let us start. So, one second. So, the electron transport chain in photosynthesis. Electron transport chain. So, this electron transport chain, while we will be talking about, the way I will explain this transport chain is based on the redox potential. So, we have already told, just to have a recap, that photosystem 1 and photosystem 2 are sitting at two different locations on the thylakoid membrane. So, essentially to say, so if you look at the slide, so it is something like this. If this is the thylakoid membrane, so say for example, here you are having photosystem 2 and at a physically different location you have photosystem 1. This is the first thing what we have described about their differences, if I had to enumerate all the differences. The second difference is something to do with absorbance of light. So, one of them is all the way up to 700, the other one is at 680 nanometer, maximum it can absorb. So, this is the second difference. There is a third difference, and the third difference lies this whole complex is sitting at a different redox potential as compared to this surf. What does that physically means? That means that the overall electron accepting power or electron donating power of photosystem 1 is different from photosystem 2, and such differences arises because of the complex and its surrounding environment, what kind of proteins are surrounding it, what kind of charge moieties are present in those proteins, and what are their electron donating or electron accepting power decides that what will be the redox potential. So, today what we will do, we will map these two systems. So, we will plot them on an axis like this, where y axis, what I am drawing now, will talk about the value of the redox potential. Okay. And so, what we will observe that photosystem II is sitting at a much more different redox potential as compared to the redox potential of photosystem I. So, for example, photosystem I is sitting here. Okay. So, then we will of course assign the values and everything, and then we will observe how when the light, say for example, light is falling on photosystem II and photosystem I, how the electron is traveling, and you will see it is an uphill transport, how the electron is traveling, and finally, how the electron is being funneled from photosystem I to form the NADPH. So, this whole journey of electron we will be mapping on the basis of the values of the redox potential of each one of these complexes which are present out here, and we will enumerate all the different kind of proteins and the different components which are making this whole electron transport chain present in the photosystem. So, moving on to the next slide. So, in order to map, as I told you, so I am just putting the values now. So, you have 0, then you have 2.2, 0.4, 0.6, 0.8, and this is your y axis, which is redox potential in volts. Okay. And volts. Now, above 0 exactly same way this will go on. So, these are in the positive values. So, minus 0.2, minus 0.4, 0.6, minus 0.8, minus 0.8, minus 1, 1.2, 1.4, likewise and so on and so forth. Okay. So, the scale is now ready. Now, if you look at the redox potential of water, redox potential of water is out here. Now, we are just placing the different component which are involved in it. Okay. Very interestingly, as I told you, in the photosystem II, there is something called a manganese cluster, which we will be talking about water splitting. The redox potential of manganese cluster is more positive than that of water. What does that physically means? That physically means manganese cluster can pull the electron from the water much more easily. So, if I had to place the manganese cluster in this scale, you will see the manganese cluster will be sitting somewhere out here. Just So, somewhere out here you have the manganese center or manganese cluster, whatever you call that. Okay. Which has, so the electron will flow like this given a situation. We will talk about that why the electron flows like that, and from here there is a complex called Z complex, and this is where it can, this is the P680 or the photosystem II. So, remember we talked about in the just earlier we talked about that, one second. So, P680, which is essentially showing the photosystem II. So, what is happening here is, now again coming back to the so light is falling, light falls here. Once the light falls here, after this series of electrons are excited, and they are excited all the way up to almost up to 1, or rather somewhere out here. So, this is where the P680 excited state electron chlorophylls are sitting. So, there is an electron So, light falls on the chlorophyll molecules at P680 at photosystem II, the electron is ejected. This electron all the way move having a redox potential of -1 volt. Okay. So, it has already shoot up. So, now what is the situation? Situation is that at P680 you needed electron in order to bring that chlorophyll molecule back to its ground state, because the chlorophyll molecule is now devoid of one electron. That electron is supplied from water molecule out here. It is this water molecule which is getting trapped into the manganese cluster. In the manganese cluster, what is happening is there is electron which is generated, which moves here, it generates proton, which generates the proton gradient, which leads to the proton gradient, and the byproduct of this whole process is oxygen. And we will talk about this reaction, how this reaction happens. Okay. But essentially what is happening, from the water, the electron is being taken up by the manganese cluster and is funneled to photosystem II, which is out here. So, the electron which was ejected by the chlorophyll molecule of photosystem II has reached a redox potential of -1 volt, but that chlorophyll molecule which lost that electron comes back to its ground state because the electron is supplied by the water molecule. So, once again just follow me. So, P680, which is photosystem II, gets excited, the chlorophyll molecules eject out electron, the electron travels all the way to -1 electron volt of -1 volt of redox potential. The chlorophyll molecule, which is now devoid of or which is almost oxidized because of losing an electron, is brought back to its ground state by obtaining an electron. Who supplies that electron? Simultaneously underneath photosystem II, there is something called a manganese cluster or a water splitting cluster, which traps the water molecule, squeeze out the electron, supplies it to photosystem II, and in that process it generates a bunch of protons, which creates a proton gradient, and simultaneously the output of that reaction is there is oxygen which is liberated out. Okay. So, up to this it is clear. Now, what is happening to this electron which has gone all the way up at -1 electron volt. Okay. Now, let us follow me with the slides. So, from here it starts donating the electron to nearby, just let me mark the 0, that will be easy for me to follow. Okay. So, it donates the electron to a nearby molecule called pheophytin, pH. Okay. From here it donates to QA, and I will tell you what exactly that does that mean. From here it is donating to QB, then it comes to QH2. These Qs are nothing but these are called quinones. Okay. And from there it comes to something called cytochrome BF complex. So, this is B actually, BF complex, and which is also involved in creating a proton gradient. From here it is, and by this time you must be observing that it is almost reaching from -1 volt, it is almost reaching 0.2 volt. Okay. So, it reached to plastocyanin, and the plastocyanin funnel. So, in this process what is happening? Let us try to understand it. So, out here the electron which moved, in its closest proximity there is a protein called pheophytin. Pheophytin gets reduced by obtaining that electron. Soon as it gets reduced, it transfers this electron, come back to its ground state by supplying it to quinone. Quinone gets reduced, then quinone supplies that electron to QB, again come back to its ground state. Similarly, from QB it moves to QH2. So, what is happening is that in this whole process there is an electron which is hopping down, and the molecules which are sitting out here are getting oxidized, reduced, or reduced, oxidized, reduced, oxidized, reduced, oxidized, likewise reduced and coming back to ground state, reduced, coming back to its ground state, reduced, coming back to its ground state. It is accepting an electron, and in that process it is getting reduced and then coming back. So, this whole thing, so you can imagine it is almost a continuous wire of different kind of proteins which are present there, which has the ability to accept electron, because you have to look on your left hand side on this, they are all sitting at different kind of redox potential and they are in physically close proximity. So, that is one of the things which you have to keep in mind, that this redox potential ensures that their electron accepting power is different from each other. So, instead for the electron to jump from P680 to QA is occluded, because in between there is physically another protein which is sitting, which is pheophytin, which has a different redox potential, which allows it to extract the electron much more faster, much more better than the next one. So, what is happening is that in this whole process the electron is following a staircase, as if the electron is jumping the staircases the way we jump through the staircases. But now think of it, the electron could have followed another trajectory, electron could have moved like this. It does not do like that, and what is the significance of it will come later into it. Okay. In that whole process, so while this is happening, simultaneously another thing has already happened at photosystem I. So, here we have the P700 or photosystem I, PS1. Okay. So, simultaneously light also had fallen there, and the electron from here, which is ejected out, went all the way up to almost 1.4 minus 1.4 PS 700. So, this is the electron which has, one second, okay, this is where the electron is sitting. Okay. Now, this electron again follows a cascade, exactly the way this cascade you see. So, okay, fine, I will take care of it here. Okay. From here it is given to an electron acceptor A0, and by the time this happens, let me just draw another line which will help me to kind of okay, because NADPH finally when it happens it is around 0.4. So, A0 to A1, and then it comes to something called iron sulfur cluster. There is an iron sulfur AFX or iron sulfur cluster. From there it moved to something called ferrodoxin FD. From there it comes to ferrodoxin P, and from here it is given to NADP. So, this is the N strongest reductant which is formed there. So, you remember that I told you that there is a strong reductant in the form of NADPH which is formed there. There is a strong oxygen in the form of, so if you follow here, this is that strong oxidant which is formed here. This molecule is the strong reductant which is formed here, and there is another thing which is formed because of the proton gradient. So, now what we will do, so again if you look out here, you will observe the same thing which has been followed by nature, as if there is a staircase model of electron hopping down like this, and each one of these proteins, if you again map them, if you have any confusion, if you map them, you will see on that scale they are standing at a different redox potential. Okay. So, this is very critical, it is kind of an basic fundamental understanding which I want you people to imbibe, that the way nature has designed this machinery is an amazing. It is not a continuous thread of or continuous wire like a copper or aluminum wire. These are proteins which are sitting at different redox potential. Each one of them has a different power to accept and donate electron, such that the electron which is coming will prefer this one followed by the next one, and they are physically like that. So, the electron, that is why I was trying to tell you, electron cannot jump back like this, but what is the advantage it is getting by doing so? Now, the advantage is in front of you. Think of it, that if electron would have, say for example, just even we take between photosystem I and photosystem II, if you see this distance from here to here, if the electron has gone up and similarly gone down, then the time window of this event would have been this much. Whereas, here what you see, the time window has gone, so there is a time. So, you are getting a lot of time in this whole process while you are allowing the electron, though it is speed wise it is a slow process, but why nature followed such a slow process instead of making it a fast process? You can think several, of course, I mean what nature thought we do not know, but we can speculate. One of the biggest advantage by allowing the electron to trickle down like this, you are increasing the time. So, in other words, you are increasing across the membrane, you are increasing the time. It is something like, by allowing the electron to hop down like this in a staircase model, electron is hopping through, you are increasing the time window across the membrane in a way that as if there is a battery which is getting charged and it is getting discharged like this. So, the time window helps it to maintain a polarity across it for a longer period of time. Simultaneously, this polarity helps to funnel the protons across in a gradient, because you are maintaining a voltage gradient across the membrane by allowing the electron to move slowly, and this helps to maintain a proton gradient, and which essentially leads to the formation of the ATP molecule. Now, what we will do? We will talk about the physical structure of the photosystem I and photosystem II. So, physically if you look at it, so the physically the structure of photosystem II is something like this. For this, you people can refer to a book by Stryer, or even you can refer to a basic biochemistry textbook, where you will observe this. So, this is how the physically the structure kind of looks like. So, and this is how they are sitting on the membrane. So, you can refer to Stryer or Leninger or any of the standard textbook in biochemistry, and or Voigt. Okay. So, this is your P680 center or the reaction center, what we have already talked about. These are those quinone, QB, QA, and these are different proteins. So, this one is called the D1 unit, this one is called the D2 unit. Then you have a 43 kilodalton protein on the flanking, there is a 47 kilodalton protein flanking on the other side, and this is where you have the manganese cluster sitting, and underneath you have a 33 kilodalton protein, and there is a lot of work going on in this area to get a single crystal of this kind of a structure, so as to figure out how this whole water splitting is taking place. So, this is the stromal side, stromal side, and this is the luminal side which is present there. So, this is what we talked about is photosystem II. Now, photosystem I we look about. So, photosystem I is also similar. So, you have these lipid membranes on which these are embedded. So, you have this big chunk which is called PSA-A, and you have the other side which is PSA-B, you have this Fx, which is the iron sulfur cluster which is present there. Underneath you have this A0, you remember this A0 we talked about. You have the A1, these are the electron acceptors, and here is the main reaction center P700 which is present there. Then underneath you have the plastocyanin PC, here you have PSAF, and of course this is the lumen, and here you have the lipid bilayer which is sitting there, and on this side you have PSAC where you have CFA and FB, which is the ferrodoxin complexes which are present there. Then you have PSAD and you have FD, which is the ferrodoxin. Okay. So, physically this is how the structure looks like, and if I had to draw this whole thing in one platform, it will look something like this. Let me get back to the slide, which will help you to kind of understand how that structure will look like. So, okay. So, this is how the whole thylakoid membrane structure looks like. Okay. Here what you are having is say photosystem II, where the light is falling, H nu, and this is where quinone to QH2 and all that transport taking place, and so you have the cytochrome BF complex sitting in between. This we have already, I have shown you this whole thing on the scale of redox potential. So, now I am just physically drawing it. So, you have photosystem I sitting here, which generates NADP plus to NADPH, which is going to the Calvin cycle or the dark cycle, and out here I told you this, so there is a proton gradient which is formed here, there is a proton gradient which is formed here, and there is another proton gradient, and out here underneath it you have this 2H2O forming oxygen plus 4H plus, which is the protons basically, and this is the thylakoid lumen. And underneath out here you have this interesting structure called ATP synthase, which is converting the ADP plus Pi to ATP, and this is regulated by a proton gradient which is funneled by all sorts of protons which are coming here, H plus, and lot of this H plus which are coming here. So, this is where the another aspect what I was telling you is the ATP synthase and ATP formation taking place. So, let us number them. So, you have the NADPH form here, you have the oxygen form here, you have ATP which is a weak as well as strong reductant is formed here, and out here the electron is transferring from out here. Okay. So, this is the whole scheme of things if I have to put it in one platform to see how this whole process looks like. Okay. So, let us again scroll down what all we talked about. We talked about for the structure of the photosystem I and photosystem II. We talked about their differences, then we mapped them based on their different component on the scale of redox potential and how the electron is hopping slowly from one step to another step to another step, and likewise and so on and so forth. And now, what is left for us to figure out Very briefly, we will spend next 5 minutes to talk about what is happening here, how this stuff is getting evolved as compared to the other stuff. Like, because I told you that there are two processes which are happening out here. So, but how this process is taking place. So, regarding this manganese cluster, let me tell you that though we know a lot of things, yet we do not know much about this structure, because it is very, very tough to get a single crystal of manganese cluster. It is exceptionally challenging as of now, but what we know is there. So, I will just put one schematic for you, what possibly happens, or at least documented in the textbook, and for that you people can go through the bioinorganic chemistry chapter in Shriver and Atkins. It is an inorganic chemistry book by Shriver and Atkins, and I will just put the picture for you people to have a look at it, just the same way I suggest you. You can go through Stryer, you can go through Leninger, there you will get an idea. Similarly, through Shriver and Atkins gives you an fair idea what is happening. So, before I draw this, just try to understand what happens in this manganese cluster. So, manganese cluster, there are manganese, there are at least 4 known, manganese atoms which are sitting there at different oxidation state. So, manganese oxidation state varies from 2 to all the way to 6. Okay. But here the manganese atoms are sitting, and it is very tough, because we are living in an oxygenated environment. Most of the time you will see manganese at a higher oxidation state, they will be at 6, because it is getting oxidized, because in the presence of air. But in the manganese cluster, these manganese sits at a lower oxidation state, which is thermodynamically very challenging to achieve, but it does, some way or other it does. And in a close proximity, there is a tyrosine molecule coming from one of those protein complexes, what you see while we are drawing the photosystem II. And some way or other, we do not know how that really happens, 2 water molecules get trapped into it. And then what happens is that it splits up the 2 water molecules in a very unique way by moving through at least 4 sets of reactions, and what we get an output as an oxygen coming out as a byproduct, and bunch of protons, what we have already documented in the slide, and bunch of electrons. So, I will just draw it for you to just to give you a feel exactly how the manganese cluster as of what we know. So, I told you that there are 4 manganese which are almost arranged in a C kind of fashion, something like this. Okay. So, these are the 4 manganese atoms. So, now the water molecules. So, what you see here OH2, here you have the OH2, and in a very close by, so you have a tyrosyl residue or tyrosine residue which is present there, the oxygen like this. Okay. So, this is the tyrosine residue. I am not getting into the complex drawing of it. So, now, so this is how it looks like, and there are different stages, different phases which are being numbered as S0, S1 and so on and so forth. So, the first reaction what happens out here is electron is being ejected out and a proton is being ejected out, and what you see is in the S1 phase is you have of course the cluster sitting there. So, I am not redrawing this cluster again. So, this cluster will continue in all my drawings. So, I am just putting it like this. Okay. So, what you observe is you have on this side you have OH, the other you have OH2. So, what has happened is that one hydrogen has gone out. So, now next stage from here, which is we are reaching into the S2. At the S2 again, now looking at the structure, okay, and this is what you observe. You have a OH, you have a OH. We are into S2 and in that process simultaneously here you have another electron and another proton which has been given off. Now, from here we move on to S3 phase, which is S3. S3 is again okay. Out here again what you are having is OH and a very unusual situation having an O, and while doing so there is another electron and a proton has been given up. Now, from here we reach to the S4 phase, which is the final phase of it, which is what we observe is they form an oxo bridge out here, it is called O out here, O, O. So, the this complex is where oxygen is being liberated out. So, what you see out here, this oxygen is being liberated out, and while going through this phase you have another electron and H plus which is giving out. So, if I have to count all of them, so the oxygen is giving out, and this is where I told you that 2H2O, the cycle continues. So, 2H2O is fed to the, or 2 molecules of water is being fed to the manganese cluster. They bound on the 2 ends of the C's, as you could see, and from there on it slowly split those 2 molecules in 4 different. This is what we know as of now, but in future if a single crystal structure comes and one can see really this is what is happening, then it will make more sense. So, as of now this is based on X-ray data, whatever little bit of an X-ray data what we have available out here. So, essentially most of these data are coming from X-ray spectroscopy. So, what it basically says that, so owing to the lack of the single crystal, the detailed structure of the clusters are unclear, but the sheath-shaped oxo bridge or Mn4 arrangement is indicated by the X-ray spectroscopy, or it is also called EXAFS. So, coming back where we diverge into this whole domain, I told you that there are 2 aspects which is very important for you people to understand from the bioenergy perspective. One aspect is the formation of or the splitting of the water in the photosynthesis, which in itself is a big domain where people are trying to emulate the manganese cluster, because then we will have abundant of water on earth and we can utilize the hydrogen which is liberated out from the situation, and from here you can make a fuel cell by having those protons and passing it through Nafion and all those kind of things, proton specific membranes, you can make hydrogen. Okay. That is one route. We will talk about this in the advanced technologies. The other route, other part of the reaction, if you remember, now going back to that reaction again. So, the basic reaction where we started, this whole was CO2 plus H2O, CH2O plus oxygen. So, now you people know how this reaction is taking place. What you do not know, how this reaction is taking place. We will talk about this reaction next. So, this is what we talked about, the whole manganese cluster and the governing by light energy and cascading through photosystem II to photosystem I, the cascading of electron and generation of ATP, and finally to run this show we have NADPH. Okay. So, we will close in here with this overall background of the light reaction, and our tailpiece will be to talk about the dark reaction, where we will talk about how carbon dioxide is fixed, which is another. So, there are 2 big, one of the biggest areas in bioenergy is that carbon dioxide fixation or carbon dioxide sequestration. So, that falls under that part where we will talk about how the CO2 molecule forms those wonderful carbohydrate, and what are the significance in terms of C4 and C3 plants, why C4s are more efficient as compared to C3, what are those reactions. But what you have to understand here is there are two aspects to this. One is the light reaction, one is the dark reaction. So, now today we are concluding the light reaction of photosynthesis, where we talked about the whole architecture of photosystem in terms of photosystem I, photosystem II. Photosystem II is having a manganese cluster underneath it, which is of course considered as part of the photosystem II itself. When the light falls through reaction center, the electrons are funneled out from the chlorophyll molecules from photosystem I and photosystem II. But having said this, this will bring you to a very different kind of a, are these two electrons different? So, you see there is one electron which is travelling out here, there is another electron travelling out here. Are of course, when you talk about electrons, it is just an electron, but are these two different kind of electrons? Are these different kind of waves of electrons or particles of electrons moving out? Because they attain a different kind of redox potential. Okay. So, we talked about the location of the photosystem I and photosystem II in terms of their spatial location, their redox potential, and then we talked about the hopping of the electron and how the whole oxidation reduction or the redox chemistry governs the flow of electron in a slow pace in order to allow the set of reactions which includes, so the formation of the ATP out here and the NADPH, as you could see out here, the output is the oxygen, and of course funneling it to the dark reaction. So, next class we will start with the dark reaction and we will finish off the whole part of photosynthesis, which will lay the foundation stone for the biomass formation on the floor of earth, followed by next phase we will move, we will talk about the processing of the biomass. Thank you.